now is move on and do something on thermal processes, thermal desorption. Okay, so in thermal there are two basic processes one can have. One is a desorption process, the other is an incineration process. A desorption process is where you take the soil, you heat it to a particular temperature, and you get the contaminants out of the soil and then dispose the soil. Okay, so it's done at a lower temperature compared to incineration. Incineration is when you take that soil and you completely burn it. It becomes ash. The soil and the organics and everything is burned. Okay, needless to say, incineration is more expensive. Okay, so if you have a hazardous material, you have you don't know what it is, fairly hazardous material, you don't want to desorb, because once you desorb it, you still have to treat it, right? And if you don't want to be dealing, good morning, you don't want to be dealing with the desorbed gases or something that is coming out, then incineration is a way to go. But it is an expensive way of treating soil. Okay, because you are burning everything, including the. So let's look at desorption here. So the principle of desorption is to vaporize contaminants from the particles. Okay, to remove and then to remove the vaporized contaminants. As you can see, so the first stage is to excavate. Okay, then you start to differentiate between what has been the larger size particles. So like you excavate things like rocks and roots and all that, things which have been in location which are much bigger than a regular soil grain, right? So you take those oversized rejected material, you either send it to a landfill or you can pressure wash it, or there's a separate way of treating it. Then you take the soil and you let it go through a desorption process. Okay, when you desorb it, you would eventually come out as a gas phase and the treated soil. The treated soil is, hopefully everything is removed from that soil, and now it becomes if everything could be desorbed, has been desorbed and removed, then you can actually dispose it at that location. But if it contains other stuff, for example, if you have a mixture of contaminants, let's say a mixture of certain metals and hydrocarbons, okay, you can use a thermal desorption to get rid of the hydrocarbons, and then the metal contaminated soil, which still you need to deal with, maybe you can consider things like solidification at that stage. Okay, so it's a two-step process for the scenario that we just talked about. Then the gases, so that's the treated medium. Now the gases, you can send it through activated carbon. If it is just hydrocarbon, you can use a burner. There are different ways of treating it. We saw that in the previous lectures. Okay, are you with me on that? So basically that's what desorption would. So the contaminant desorption depends on, now let's look at the desorption phenomena. What does it depend on? It depends on the temperature of desorption. Okay, what temperature are you desorbing? Of course, the higher the more heavier the hydrocarbon, the more higher the temperature you might need. The matrix itself, okay, if you have sandy soils with hydrocarbons in it, it's a lot easier to desorb sandy soil, let's say dry, if on as compared to, let's say, clay soil with lots of moisture in it. The clay will stick to the inside of the desorber. The moisture requires a lot of energy to be taken out. Eventually, you might find it it might become expensive, and it might even be cost prohibitive. The contaminant characteristics, right? Like what is present in that soil. Now, if you desorb it, you have to deal with it, right? Because now it's in the air. You have to actually collect the gases, and you have to make sure you have the wherewithal to actually treat the gases. And the moisture content. Too much moisture will eat up a lot of energy, and maybe desorption is not the way to go, or you may have to pre-treat, get the moisture out, and then dissolve. Okay. After you have dissolved it, you may have to do the toxicity characteristic leaching procedure test to determine proper disposal. And as we talked about, thermal treatment of fine-grained soils like clays and so on, moisture about plastic limit is difficult, which means the soil has got lots of moisture in it. It is not easy to do that. So this is an example of a typical desorber. You got your contaminated solids coming in. You have your primary treatment unit. In this particular case, you can see the whole unit is being heated. Okay, the whole unit is being heated. So there are two types of desorption you can have. One is a direct fired, and the other is a direct fired, and the other is a indirect fired. Okay, so in this particular case, this looks like that it is being directly fired, which basically, indirectly fired. You are heating the cylinder here, and then it goes to your off gases that comes out. Now think of what the gas would comprise of. It's not pure gas. You'll also carry some. It's very dry. You'll also carry some flue material. Okay, like solid particle. So you may have to go through a cyclone to separate the dust particles from the gas itself. Okay, then it run through an oxidizer where you oxidize the gases, you cool it using a quencher, eventually filter it, and then vent it out. Okay, are you with me on those steps here? So you need to make sure that your treated gas, so whatever comes out of the cyclone at the bottom, you know how a cyclone works, right? You take that gas, send it through a cyclone, the solid particles falls to the bottom, the gas will go to the top. The solid particles, the dust particles that come through the cyclone still needs to be collected and sent, right? So that's where it's collected. You add water to clean it, to cool it down, and then dispose of the clean solids. That's the basic mechanism of it. There are different types of desorbers. Rotary desorber, like direct fired, indirect fired, and heated conveyor systems. Those are the three kinds of desorbers we have. A direct fired is basically what you do is you put everything in one cylinder. Okay, you put your contaminated soil as well as the fuel within one environment. Okay, so let's say you saw those drums, right? You put like big steel cylinders. You bring your contaminated soil in there. You bring your fuel to heat up, right? You need fuel because the amount of hydrocarbon that is present in the soil may not be sufficient to give the fuel that you need. So you may have to add the fuel, and everything is put in one place and heated. Okay, so in a direct fired, you got pre-treatment, and then you got pre-treatment is again what we talked about earlier, removing the bigger size material. A desorption unit where you dissolve the gases, and a post-treatment which is basically collecting the solids. The solids are then disposed of in along with the clean soil. Okay, so that's a post-treatment. So on the pre-treatment side, you have to have a canopy cover. This is basically things like you want to make sure the dust doesn't fly around. You want to also make sure that that if you have dust, it's a big operation. If you have a rainfall event, then it doesn't run to some run off ground and so on. So you have to protect that particular contaminant. So that's true with most of ex situ treatment, whether it is soil washing, whether it is the moment you dig it out, you have owned it. It's yours. You have to protect. You see, if there is a rainfall event, you want to make sure that it doesn't carry the whatever is coming out from there to the water bodies nearby. The maximum solid concentration, so maximum particle size is 5 to 6.5 centimeters. The contaminant characteristics, the contaminant concentration has to be less than 25% of the lower explosive limit. If you have too high a hydrocarbon in there, you might have an explosion inside. You don't want that to happen. So that's something you need to make sure that the concentration of the contaminant is less than 25% of the lower explosive limit. For tar-like contaminant materials, you have to, you may have a handling issue. The thing might, once you heat it, tar, it's inside the desorber, you have an issue with that. So highly acidic medium has to be treated with lime and so on. So those are some of the issues that one needs to consider. This is logistical. So you can have a desorber which can be co-current or counter-current. What it means is let's say you have a cylinder like this. Okay, and you can put your contaminated soil coming through here. That's your contaminated soil. Okay, and you can put your fuel as well here, right? The fuel. Okay, and they both, when they come out from this side, whether it is the soil or the burned gases, that is known as co-current. Okay, that is co-current. They're both going in the same direction. What is the other one is a counter-current. Okay, counter-current meaning you get your fuel to come in here. Your clean soil comes out from there, and burned gases might come out from this end. Okay, this is a counter current. Okay, this is counter current. So what's a possible advantage or disadvantage of a co-current compared to a counter current? Why do we need to worry about whether we should have co-current or counter current? So co-current, so if you look at just the counter current, right? Think about what's happening. You got your contaminated soil coming here. It is getting fired up. When it leaves here, it is relatively hot, right? So there is a little bit of a, not little bit, but there is a significant amount of heat that can be utilized by the fuel to heat up. You have a heat exchanger going, right? In some form, you are exchanging the heat here, and then so the fuel can be heated up as it goes inside there. So counter current, so the co-current, in counter current you would have heat being extracted from the gases as it comes out. Okay, because you would have the clean soil and the gases coming from the top here. The gases are hot, it'll heat up the fuel. You won't have that facility advantage in co-current when everything cold is going in one side. Okay, the colder temperature in the bag house for counter current. The other thing is, because you are extracting the fuel here, the fuel is extracting some of the heat here, the gas that comes out here is cooler temperature than if everything is going in co-current and everything hot comes on the other side. Okay, so the gas is colder. What is the advantage of gas being colder? Remember what happens after the gas comes out. It contains a lot of particles, right? So to remove the particulates, you want to send it to a bag house, right? A bag house is just a bag with, it's like a filter, right? Now, if too high a temperature, if the gas contains the gas temperature and the particles are at very high temperature, the bag house might catch fire. So in a counter current, because the gas is colder, you can just have the bag house. In co-current, because the temperature is so high, you can't just have a bag house. Then you may have to burn everything and then cool the gas and let it go through a burn. through a baghouse. So the configuration of how you treat the gases after it comes out is also dependent on whether you use a co-current or a counter current. Okay, heavier organics may condense in the baghouse. That's another one that post treatment we've got solids, gases. If you have organics, we can use afterburners, catalytic oxidizers, carbon adsorption systems, and we saw some of them when we talked about it a couple of days ago. Afterburners can be ceramic or operated between 760 or 980 degrees Celsius, and so on. I'm going to move on here. Rotary desorber, which is indirect fire. So that is direct fire, where everything is put in one environment. Okay, an indirect fire is where you put your gases, put your contaminated soil in a particular container, for lack of a better word, and then you heat the container. Are you with me on that? So instead of putting everything going in through this one as it is shown here, what you do is you would heat this itself, right? You would heat this. Okay? So what is the implication? So that's an indirect fire, okay? You're indirectly firing it. What is the implication of that? The implication of it is so let's compare direct with indirect. What did we do in direct? We put everything together and we heated it, right? So the fuel, the gases that came out of the fuel also needs to be treated because they're all mixed together in a direct fire, right? So the fuel is CO2, whatever is burning out is all, now you have to treat it. In an indirect fire, you don't need to treat, this is all your fuel. You don't really need to treat the gases that come out after, from this one. You only need to treat the gas that comes out of this one here, right? So there is a cost implication there too. And of course the material is different. This has to be steel as compared to ceramic that's used in the other one. Less than 40% moisture content, because of course if you have too much moisture you would have boiling kind of a situation. Other than that, I said that lower volume of exhaust gases and some of the feed rates we can ignore. So you can have one of these two scenarios. You can have a direct fire, you can have an indirect fire. You can also have what is known as a heated conveyor. It's basically a conveyor belt. Okay, you put your soil on it and the belt is heated, or if it's a belt or if it's a screw type, then the screw is heated as well. Okay, you guys are familiar with the screw thing? So it's like a big screw. Okay, you put your soil in one end, and as the screw rotates and the screw is heated, think of a screw, a big massive screw. Okay, so and how does the screw go? It's got these threads, right? And it has a big, and as the soil flows from an end where it has, and the whole screw is heated. Okay, as the soil flows through those threads, right, the heat causes the gases to get dissolved from the soil particles, and the soil comes out at the other end. Am I clear on the screw? I don't have a picture of the screw, but think of a screw, a massive screw, and your soil in the grooves of the screw. Okay. Again, typical particle size between 2 to 3 inches, because you don't want the screw to be, jam, because you have a big thing. A retention time somewhere between up to 90 minutes. I have a video that if I can show, I will show. It'll give me 2 minutes. If इसको बंद कर दीजिए अब 2 मिनट के 10. In the thermal processes, you can have either a desorber or an incinerator. An incinerator is something that is used for heating and burning the entire soil and everything that comes with it. Okay, and there are materials like that where you may not like to desorb or anything. For example, hospital waste. If you know in the past something had happened and hospital waste, like best thing is send it to an incinerator, let everything get burned, and don't worry about trying to desorb and treat or anything, because there is a when you do anything, right? But desorption also has a place, lower temperature and of course lower cost. So on the desorption side, you can use a direct fire desorber, you can use an indirect fire desorber, you can use a screw desorber or heated conveyor or a screw desorber. Direct fired, so in any case you will have off gases which you need to treat. If you're desorbing something that's coming out, you need to treat it. Bottom line, right? And then the soil, maybe the soil is clean, maybe it's not clean, maybe it still needs further treatment. Give the example of metals and hydrocarbons. Metals may still be there if you haven't taken, and if they're still there, you will still have to, but at least you have a dry soil to treat. And we talked about solidification yesterday. That might be the way to go going forward on that side. Okay, so it may not be treating the whole problem, but treat the portion of problem that you wanted to treat. Hydrocarbons, then you have it. You can either burn it, or catalytically oxidize it, or adsorb it. There is a whole series of options to do to treat those things. Okay, that's what it is. You saw the operation. These are big operations. Okay, these are not small operations. You don't do a small desorption. If you happen to have if that's what you want to consider, the best thing is to look for a contractor who has a desorption unit, who does desorption, and they'll bring the stuff to the site and do it. What is this noise? Can you hear a noise? What is it? Anyway, so I'm not going to move on to what is this soil chemical oxidation, or ISCO as it is called. Okay, so this the purpose of ISCO is to oxidize the chemicals that are present in the soil. Oxidize the hydrocarbons that are present in the soil using chemical methods. Okay, and in situ meaning no, not on site. On site, that you can have ex situ on site. Take it out, do it on site. That's ex situ on site. So in situ means at location. So, okay, but you can do it either at location, or you can take it out and do it on site, but it's ex situ. So the criteria for selecting an oxidant, what are the criteria? How do you select an oxidant? You want to make sure it has enough oxidizing power. It has enough juice within itself to oxidize what you want it to oxidize. First, all right. Second is it should be non-toxic. You don't want the oxidant to actually become a problem. It should be available at a reasonable cost, and it should be low cost for commercial application. Because you need large amounts of oxidant, and if you're using a large amount of oxidant, it better be at a cheap cost. It should be easy to handle. It should be easy to be brought in and applied. You don't. So keeping all that in mind, we can look at some of the oxidants that are used. Some of the more known oxidants are hydrogen peroxide and Fenton's reagent. Okay, hydrogen peroxide is H2O2. H2O2 is an oxidant which is used in both in water treatment as well as in soil treatment. When you add hydrogen peroxide with iron 2 salt, okay, it gives rise to hydroxyl radicals. So one of the main things about an oxidant is trying to utilize these This is what is known as a hydroxyl radical. Okay, these are short-lived radicals, very short-lived, okay, that are very potent. Okay, unfortunately they are short-lived, but they are very potent. They can oxidize things quite quick. Okay, so hydrogen peroxide. So if you add hydrogen peroxide with Fenton's reagent, you will get some of these, and that's one way of oxidizing. You can also use permanganates, which are oxidants as well, potassium and sodium, and you can use ozone, which is a gas, but it's a very strong oxidant by itself. There's another one called persulfate that has been used, also provides pretty good results. The bottom line is you want to make sure that you oxidize with whatever you're trying to oxidize, you oxidize. So let's look at this one first. Here, hydrogen peroxide, Fenton reagent reaction chemistry. Alone H2O2 has an oxidizing power relative to chlorine of 1.3. Okay, so if chlorine is 1, H2O2 is 1.3. But when you combine it with iron 2 salt, it gives rise to this radical, as you see in that equation there, right? H2O2 plus 2Fe2 plus gives Fe3 plus OH minus plus hydroxyl radical. That's a general equation. Okay, there is a bunch of other steps that go in that, and we can ignore those steps for the time being. But look at the oxidizing power of OH radical is 2.06. Compare that to chlorine, which is 1, and H2O2, which is 1.3. So just by looking at it, you can see that OH is a much more powerful oxidant. In fact, it is the second most powerful oxidant known to us. Number 1 is fluorine. Okay, but we can't use fluorine, right? Too reactive. So it's pretty good. The problem is it's short-lived, right? And the second problem is it's non-specific. Non-specific meaning it will oxidize whatever it can oxidize. It's not going to worry about, I want to oxidize only the hydrocarbon, because if there's soil organic matter, humic material, it's going to get consumed. So that makes it that you need a lot of hydrogen peroxide and hydroxyl radicals, because you might have 90% humic material and only 10% of your contaminant. Humic material will also consume all the, you need a lot more of it. Okay, but hydrogen peroxide is not that expensive. Iron is usually present in the soil, and many times they're able to harness it to get to the reaction, and it works quite well. It is a very well-known technology. Okay, use application of hydrogen peroxide to treat soils. So if you have hydrocarbons, you want to do it, that's one way to think of it. But it is not something that you should do without experience, because it can create a situation where it may not be safe. So you want to make sure you take all the precautions, or you hire a contractor who knows what he's doing. He or she knows what he is doing. So the oxidation reaction conditions are dependent on the pH, time, temperature, concentration, presence of other organics. I told you about non-specificity. The other thing about this hydrogen peroxide ion reaction is it works best at pH of 3. Okay. Now what is the pH of soil? Just regular soil. What is the pH of that? Louder? What is the pH? In that range, right? Generally. You have some acidic soils which have lower pH, but by and large, and the thing is, soil also have what is known as a buffering capacity. If you add something to lower its pH, it will not happen, because some of the carbonates and so on that are present in soil will break down to prevent the pH from going down. It's hard to get the pH of soil down. So, and the problem is, iron precipitates out at the pH we talked about, and because so it is not that effective as it would if you can get the pH down to 3, which is not feasible. But having said that, it still oxidizes you take hydrogen peroxide in large cylinders, you have these long pipes with under pressure, have people inject it, and then it goes in under pressure, you apply it, and it oxidizes everything, and then you go on. Okay, that's the way they apply it. So it is a and it does not work well in alkaline environment. Effect of H2O2 addition on biological activity. Now the other thing is, remember, H2O2 can provide some level of disinfection, right? So it can adversely affect the microbial population. It's going to oxidize the microbes too, right? So if you have soil microbes, if you have too much H2O2, the soil microbes might be dead. Having said that, H2O2 breaks down to O2 and H2O. So those that survive will have oxygen now. Okay, so the whole reaction is exothermic, which means gives out heat and gas, and that's what I said. If you see the application of H2O2 in the site, you may find fumes coming out and gas and all that, and it's not a, it can be a little bit daunting if you haven't seen it before. So that's why you need to take adequate precaution and hire a contractor that does this and knows what to do when. Presence of competing reactions by free radical scavengers, such as, that is the other thing, presence of carbonates, bicarbonates, other organic matter, they're all going to scavenge or eat up the hydrogen peroxide's oxidizing power, and therefore the amount that you need is a lot higher than the amount that the amount that you need is a lot higher than what you actually need based on the chemistry of it. Okay. But the advantage of employing hydrogen peroxide, it's low cost chemical, right? Not that expensive. It's a rapid reaction process. It happens, and that's it. It's applicable over a wide range of volatiles and semi-volatiles. It's very versatile in that sense, and there is significant field experience. There's lots of people who have field experience in applying hydrogen peroxide who can give you proper advice and actually do it for you if you pay them their thing. So this is a system where you can see, you apply chemicals in the in the three. So this one is an illustration. You apply your the oxidant through those three pipes, as you see. It goes out and through those the holes on the side of the pipe and does its job, and then pretty much that's what it is. So you don't have to actually take the soil out. You don't have to treat it anymore. You just inject it. Just put it in. Put your pipe in. Apply under pressure. If you apply enough pressure, you may even be able to fracture it, which if you need from let's say from the soil condition that you need some fracturing, you can fracture the formation, break it out, and apply the hydrogen and force the hydrogen peroxide into the pore spaces, and hydrogen peroxide will eventually break down to H2O and O2, and the O2 is beneficial in getting the dissolved oxygen concentration up and getting some biological activity going in longer term, and whatever it can oxidize, it oxidizes. Got it? Any question on that? Then there is the permanganates. Okay, potassium permanganate. So it has an oxidizing power, as you see, a little bit lower, 1.24. It is used to treat drinking water and wastewater as well. So is hydrogen peroxide, by the way. The problem with this one is so let me not talk about the problem first. Let's start with MnO2. Generally is not a concern except for precipitation. So if you look at that equation there, MnO2 is formed, the permanganate MnO4 reacts with the radical to form MnO2, and okay, MnO2 particles forms as precipitate, and once it forms precipitate in the subsurface, it's going to clog the pores. Something to think about. Okay, and has been successfully applied for alkenes, aromatics, phenols, pesticides, chlorinated compounds, and so on. Okay, now you see the color? What color is it? Magenta. I was going to say pink, but let's go with magenta. Thank you. But this is the problem. It gives this color. Okay. How would you like your groundwater to have that color? Pure, nice pink color. Okay. You don't like it, right? Color is a problem. If you use it for water treatment or anything, that can be an issue. Okay. But otherwise, it is used for TCE quite a bit. TCE, remember I talked about the other day. It's a dry cleaning. It has been used for dry cleaning, PC and TCE, and there has been a lot of it has been used quite effectively. So permanganate is something, don't scoff at it. It's a pretty good oxidant. It does a good job. It does not have some of the problems that you have with hydrogen peroxide. For example, the oxidation reactions are not exothermic, so it's not going to produce heat and gas and all that you have to deal with H2O2. They are readily soluble in water and has a high efficiency. They're relatively safe to handle compared to what we talked about. Not much of pH control that is required. And presence of free radical scavengers. Radical scavengers are something that scavenges out this. It's not such a big issue. Neither oxidant nor byproducts are toxic to microbes. So it is effective. Lower oxidizing power, but it has some benefits to itself. Some of the disadvantage, the color. Okay, and then deposition of MnO2 in the pore space. You will have to remove the color somehow after this. Right. Okay, the next one is ozone. Okay, the ozone. How is ozone produced? What is ozone? What is ozone? Louder. O3. And how is ozone produced? How is ozone produced? So we basically 3O2, correct, right? If you apply electrical current, what? No? So that's how. So you apply an electrical current and you let air go through between the electrodes. The oxygen molecules will turn into ozone. Okay, that's the very simple formation of ozone. Okay, it is a very strong oxidant. Okay, ozone is dangerous in that sense. It will burn your skin, it will burn your eyes, and you breathe into it, it will burn holes in your lungs. It's an absolute. You have to be very careful how you handle ozone. Okay. The advantage of ozone is that you can produce it on site. Like hydrogen peroxide and others, you have to bring it, you have to store it, and you have to have cylinders, all that stuff, right? Here, you bring your ozone generator. If you want to use ozone, you plug it, it will produce ozone. And then you don't need the ozone, unplug it, you don't need to produce anymore. So that is that advantage. Okay. It has been used for vadose zone treatment. Remember, it's a gas, and if you have hydrocarbons in the vadose zone, you can inject it and it will do the treatment. The problem is this: you want to make sure that the ozone does not get into the neighbor's house, or there's somebody standing there and it's a crack. And as I said, it is a very strong oxidant and dangerous gas in that sense. You want to make sure that you take adequate precaution, that there's nobody around, and you give enough time for ozone to actually act as well as dissipate out. It has a half-life of about 20 minutes, so it will be there for a while. Has been used for LNAPL in the capillary fringe. Problem is it's unstable, so that can be both a problem and a benefit. Problem because you have to continue to produce it. benefit that, once you leave the site, it's not, and after a period of time, most of it is dissipated out, right? It is highly reactive. It is effective around near neutral pH, but more effective at acidic pH. Okay, so this is another one that now look at ozone injection in ground. As you can see in that figure, you inject it, it comes to the from the bottom up. But all you need to do is make sure that and this is an example where it's being treated below the water table. Okay, so if your water table has got, let's say, gasoline or napple, L-napple, you can inject it, even D-napple, and you can inject it and let it act. All you need is to make sure that the ozone doesn't cause a health impact to somebody living nearby or working or hanging around, whatever, right? The advantages of ozone: it's an on-site oxidant generation eliminates need for shipping and storage. You bring your ozone generator. It's innocuous if you don't generate it. The moment you want it, you plug it in, you generate it, you do your thing, and then you unplug it and you go home. There's minimal degradation during injection. It doesn't happen. Contaminants break down to simpler ones which can be easily biodegraded. Provides oxidation and biostimulation. The other thing about ozone is it breaks down to form oxygen. One of the things that ozone would do is oxygenate the water, right? Once it breaks down, so your dissolved oxygen concentration will increase. Okay, and it is definitely ozone treatment. So you can get biodegradation happening after you have left the site because the oxygen content has gone up, right? And it's obviously more rapid than geological and hydrogeological effects of ISCO. Selection of appropriate oxidant and delivery. Effectiveness depends on selection of appropriate oxidant and delivery. What is the appropriate oxidant? Remember, it's a chemical reaction, and like any chemical reaction, they're specific to. So in your subsurface, you got all kinds of stuff. Natural organic matter, sulfates, carbonates, whatever that might present, and you want to make sure that they don't consume your oxidant, or if it does, that it does not actually, that's something you can live with, right? Physical setting of the site regulatory constraints, presence of underground utility corridors. If you have something like a pipe or something, and if you apply ozone, it might go along the pipe, or if you apply hydrogen peroxide, or it might go along the pipe and might be a problem somewhere else. Site organic content and other geochemical considerations and physical and chemical heterogeneity. Okay, oxidant delivery mechanisms. You have surface application, you have injection probes, you have horizontal or vertical well flushing, and you can also mix it in soil. Just have a soil, mix it, mix it with an auger, and like you saw the permanganate picture, right? So let's see if I have this one now. Oh yeah, this is a Genesis video. You should watch it.
I'm Dr. Jeremy Bernstingle, Managing Director of Regenesis Europe. On behalf of the entire company, I'd like to talk to you about what you should know about the chemical oxidation of groundwater contaminants. In situ chemical
oxidant for your case, you need to make sure that you have that the after effect you deal with. So for example, if you're using hydrogen peroxide, then you've got you got your water that will be produced. If you get permanganates, then you have your color that you might have to deal with. Ozone, you want to make sure that it doesn't escape to somewhere else. So all that logistical things happen, and also you want to make sure that the oxidant is the right oxidant to be used for the condition that you are trying to use. And there is a cost comparison between different oxidants that you may like to make before you actually do it. So that's, but having said that, a chemical oxidation process is a very versatile, very widely used method to treat contaminated soils. Okay. Now let's look at engineered barriers. Okay. Engineered barriers. So remember, what is the purpose of this risk of our contaminated site management is to minimize the risk. Okay. If you can minimize the risk that a site poses, you might get a lot of flexibility from your regulator, the pollution control boards, with regards to how much time you have and what you want to do. Okay. One of the ways to minimize risk is what is called an engineered barrier. Okay. So an engineered barrier, so if I have a contaminated site like that, okay, from the plan, all right, the plan view is like that. Okay, this is your plan. What are the options I have? What are the things I need to do to prevent the contaminant from leaving the site? That's the first thing I want to do. I want to make sure it's confined, right? It doesn't become a problem. So what are the things I need to do for that? So this is a plan view, and then there is the cross section, right? So what can happen on the plan? You can have you can have rainfall, right? Once you have you can have rainfall here, and once you have rainfall, the water table will increase, or you can have runoff, all that, right? How can you prevent rainfall from covering it? Okay, you can provide a cover to it. Okay, you can cap it. How do you cap it? Well, you can put a nice geomembrane on top, you can put a foot of soil on top, compacted nice clay soil. Below that you can put a geomembrane, and now it's capped. So at least there's no water going in. Okay, so that's on the cap side. What about the water coming from? So on the, you may have like water coming into the plant and from the groundwater moving. You also want to protect that, right? How would you protect that? You can put an impermeable barrier around it, right? You can put a barrier layer like that, right? That's your barrier. Right? Any water that comes now will have to move like that. And if you have done your site characterization well, the water will not go through here. If your barrier is impermeable and nicely done, this water is clean. Okay? What have you done? You have managed the site. You cannot close the site based on this, but you have managed the site. So I can, if I'm an owner of a site, I might choose, put a nice cap on top, cover it with a nice barrier around it, now, and then continue to monitor. Okay, I'll put monitoring wells here, monitoring wells here, monitoring wells here, monitoring wells here, here, and maybe a few inside, and continue to monitor what happens. If I start seeing my contaminant in these wells, I'll start to get anxious and start to think about there is a problem. Okay, but as long as I'm not seeing anything there, I have bought myself a lot of time. Right? So that is the concept of an engineered barrier. Okay. What you see here is a constructed containment system. It prevents water, so you will have a vertical migration, which is the cap, and you can have a horizontal migration, which is a barrier. Okay. Now, landfills. What are landfills? What are landfills? Engineered what? Yes, you can call type of Yes, it is an engineered facility for storing your waste, dry waste. Okay, so every landfill would have a liner at the bottom. Before you construct it, you put a nice geomembrane at the bottom. You put a meter of clay soil. Make sure you have leachate collection pipes at the bottom, and so on. On the top, you have what you see there. You have a clay layer, a soil layer, and grass on the top. Okay, so that's typically a landfill cap. But if you want to, but that is only if you can create, if you before you put your waste in. You can't put a liner after you put the waste in, right? What you see here is what is known as a horizontal barrier, right? Sorry, horizontal migration. So it's a vertical barrier, okay, and that is known as a cutoff wall. Okay, do you see this? This is known as a slurry trench cutoff wall. Okay, what it means is to create that, you have few options. See this wall here? How do you create it? Basically, you dig a trench. Okay, dig a trench, go right down to bedrock. You don't want to leave it because it will go below the wall. So you cut a trench right down to bedrock, and you then create a soil bentonite mixture. You know what bentonite is? It's a form of a clay which is characteristic. What is its characteristic? Very, very impermeable. It's very, it becomes like jello. If you mix enough water, it becomes like jello. No, it does not allow permeation, right? So it's a very high swelling clay. High swelling means all the pore spaces are occupied by the soil and the water that is held. So use that feature of bentonite. So you take bentonite, you mix it with water, let it stay for a period of time, and then you mix it with soil. Okay, so the characteristic of bentonite is add water to it, it will become like jello in a way. Now jello has no strength, right? You know what jello is, right? Jelly in a way, right? So it has no strength. If you put it there and if it dries, it will all crumble, everything will be gone. So you need to put you need to mix it with soil. So you masticate it nicely. So what you do is you create on the site, next to the site, a little bentonite water soup. You prepare that and give it enough time, maybe a day or two, for the bentonite to actually take the water in, and then you mix with soil that you obtained from the cut. Mix it with soil, put it in there, get that same backhoe that cut it to mix it, place it, and then all the soil pores are occupied by the bentonite and the soil and everything, and eventually it becomes like a nice, and put a cover on top and it will remain there forever in a way. Okay, so that's your vertical barrier, which is known as a soil bentonite slurry wall. All right, now there's always a fear of this soil bentonite slurry wall to lose its moisture, dehydrate, and crack a little bit. That's why they are quite wide. Okay, they're quite wide, they're not as thin. So you may then choose, the other thing is known as a soil cement bentonite slurry wall. Okay, now we all know the characteristics of cement, right? So cement will give it more strength. So soil cement, so instead of just mixing soil and bentonite, you mix soil, cement, and bentonite. Okay, and what will the soil, cement, and bentonite do? It will have a higher integrity, higher strength. Okay, if you just put a soil bentonite, you can get permeability of 10 to the power minus 7 and